Okay, so in this video lecture, we'll be learning about source fiber coupling and the different types of noises that come in semiconductor optical sources. So the design objective of many transmitter of the communication system engineer is to allow the maximum light source from the transmitter to couple through an optical fiber. So there are chances that the output from the laser source doesn't couple to the optical fiber 100%. There are chances that a part of it gets leaked off, or there are chances that the whole of the signal can won't be reaching the optical fiber. So there are various mechanisms through which this coupling efficiency can be improved. So the coupling can be very inefficient when the light from an LED is coupled to a single mode fiber. As you all know, there are different wavelengths of light that are coming from an LED. So LEDs are not all good option for single mode fibers. LEDs are always used with multi-mode fiber. So when you are coupling an LED with a single mode fiber, there are chances that most of the light from the information source get leaked off. Similarly, if laser is used for a single mode fiber, the efficiency can be improved. So for edge emitting lasers, the coupling efficiency is typically between 40 to 50%, whereas for VCSELS, it is 80%. So a small piece of fiber may be included with the transmitter so that the coupling efficiency can be improved. So the fiber to source coupling can be improved by using convex lenses, by using micro lenses, or using a tapered fiber. By using a convex lens between the laser source and an optical fiber, we can make the light coming from the optical source converge to the optical fiber, so that maximum of the light is being converged to the optical fiber. From the source to the optical fiber is converged, so that the efficiency can be improved. The micro lens is other type of lens in which there is the lens is tapered, so that due to the tapered size, the maximum light can be coupled to the optical fiber. Similarly, the efficiency is improved. The other one is a tapered fiber. If you're using a tapered fiber is nothing but the shape comes tapered to that size of the output of the laser to that size from where the output of the laser is coming out, the beam is coming out. If it is for an edge type laser, you know where the output beam is coming from the edge. Similarly, if you have a concentration, if you know the symmetry of the laser output, and if you are tapering the optical fiber to match that output, then the efficiency can be improved. So this is a figure where you can see a fiber is fixed. The fiber is fixed using a solder joint. Then to the fiber you can see a tapered lens, and from the tapered lens you can see the fiber is being connected. So maximum efficiency is being obtained here. So in this figure you can see a convex lens being used so that the efficiency can be improved, and the other figure is that of a tapered optical fiber. So the next topic is the sources of noises in a laser diode. The first is phase and intrinsic noise. The phase and frequency noise. This phase and frequency noise is due to the intrinsic property of the semiconductor material. So this phase and frequency noise are always inbuilt with the laser diode. So eliminating this phase and frequency noise is not possible, but we can reduce it. The instabilities in operation, that is because of the variation in output from a laser diode, there can be noises. Then next was is reflection of light back into the device. So when the laser outputs is beam, then it is passed through a optical fiber. There are chances that these transmitted or output beam get reflected back to the laser. Because of that, there can be a noise, and that is called reflection noise. Next is mode partition noise. Mode partition noise is because of the different modes that propagate through a optical fiber. Next is the modal noise. Modal noise is present in lasers and not in LEDs, because in lasers you can transmit different modes. So because of the different modes that are being propagating through a laser, modal noise arises. Because of this, there can be constructive and destructive interference, and because of this interference you get a pattern, and that pattern is called speckle pattern of the interference. And these are mainly due to the splices and connectors that we use in the optical communication system, and this can be avoided by using LEDs. But the problem is that LED is a non-coherent source. In non-coherent sources, the interference is minimum, and then by using the single mode fibers, also this can be avoided. So, two mechanism by which model noise can be avoided by using LEDs and then by using single mode fibers. The next type of noise is mode partition noise. Mode partition noise arises in lasers. As you all know, there is not a single wavelength or a single mode that is coming out from a laser. There are chances that other modes also propagate through a laser, and those other unwanted modes are called longitudinal modes. Because of these longitudinal modes, there can be a noise, and that type of noise is called mode partition noise. And these mode partition noise arises due to the temperature fluctuations and internal variations of the device. The next noise is reflection noise. So when two fibers are joined for the transmitter, some light rays get reflected back to the optical source, and because of these reflected rays, there can be a noise. That noise is called reflection noise. The reflected rays will be having lesser wavelength than the outputted beam, and this can be avoided by using isolators and index matching fluids. Okay, next is amplified spontaneous emission noise. So, amplified spontaneous emission noise. These are the noise that arise during the lasing action of the laser. As you all know, the main principle behind the lasing action of a laser is spontaneous emission. So, when first to create lasing action, we require a population inversion. What is population inversion? The electrons from the lower energy level goes to the higher energy level. So at that time, each of the electrons has certain lifetime. Okay, so once that lifetime of the electron is over, it comes back to the lower energy level, releasing a certain amount of energy, and these electrons won't take part in the spontaneous emission. For the spontaneous stimulated emission, as you all know, when we are hitting the all those electrons in the high energy level with a particular energy, all the electrons will come back to the lower energy level, releasing a bundle of energy in the form of light. And that light, when we take out from a partially reflecting mirror, we get the output of a laser. But there are certain electrons which won't take part in this bundle energy. There are electrons which won't take part in the stimulated emission, and those electrons which releases energy, and that energy will be taken as noise, and that noise is known as amplified spontaneous emission noise.